Hi. In solid state, we will today start to see the concept of semiconductors, which are in between the good electrical conductors and the good electrical insulators. It is somewhere in the middle. But in order to understand the working of these objects, first we should a bit go back to the metals also, to see the band theory of metals, and then we will try to see the idea of semiconductors today with the concepts of some doping also, intrinsic semiconductors and doped n-type, p-type also. In the next lecture, we will be interested in the semiconductor devices, diode, transistor. We will also have a look at the laser, the working of laser in the next lecture. Today we will first see the basic ideas about these materials, which are widely used, very widely used, and the transistor, for instance, was one of the products who earned the three people to gain a Nobel Prize in physics. And also the semiconductor devices are very widely used in several other areas of physics. In daily life, also in an ordinary cell phone, for instance, there are hundreds of thousands of small transistor type devices, some gates, logic gates also. Even in a very simple computer, a great number of such devices are used to complete the tasks. So this is a very important part of this course, solid state, because so far we have tried to see the crystal structure and some conduction mechanisms, thermal properties, phonons, lattice vibrations, etc. Also electrical conduction, but at a very basic level. Today we will try to see the a bit more advanced theory. First we will start with the band theory of objects. But what is a semiconductor? First of all, let's try to see the range of conductivities. Let's consider a scale, for instance, such a scale on conductivity, electrical of course. Electrical conductivities of some materials, some typical values. This is a logarithmic scale rather, because, for instance, let's choose some sort of reference level, let's call it 1, for instance. Here we have something on the order of 10 to the 8 plus 8, and somewhere here we have 10 to the minus 16. So these conductivities, remember the unit of conductivity was the inverse of unit of resistivity, ohm meter, inverse ohm to the minus 1, meter to the minus 1. So conductivity, so these numbers are in terms of ohm to minus 1, meter to minus 1, and these, let's consider some two extreme cases. Let's say a very good electrical conductor, silver or copper. We leave the superconductivity to the other lectures next week. However, now see best conductors such as silver and copper. For example, silver and copper, they are not exactly at the same level, of course, but we can place them in a logarithmic scale. We can place them in the same level. So this is very good conductivity, this is very bad conductivity. Very bad, poor conductivity means very good insulation, and vice versa. This is a very good conductor, so very bad, very poor insulation. So remember that rho is 1 over sigma. So if one object, one element has a very good conductivity, it means it has very bad, very poor resistivity, and vice versa. So at the very lower levels we have, for instance, sulfur. Even further than that, we have polystyrene, for instance, polystyrene, some very good insulating materials. And somewhere because these are, let's say, 10 to the 7, 10 to the 6. So 10 by 10, these levels are 10 by 10. So here, for instance, we have 10 to the minus 15. And somewhere here, near the middle of this sort of logarithmic scale, we have the semiconductors, which we will talk about today. So, for example, the very widely known ones are silicon and germanium. So, silicon, let me write them in red. So, this is the sulfur, and here we have silicon and germanium. Again, these two also do not have exactly the same value for the conductivity, but they are quite approximately sort of equal. As we will see today, the gap, energy gap, will be seen also. So the gaps of these two materials are slightly different. And one of the very good insulators was diamond also. Diamond is somewhere here. So this is an important scale in the sense that no other property of a material has such a wide, astronomically wide range of values between the best and the worst. For example, what is this ratio? 10 to the 8. So the ratio of the best conductor to the conductivity of the worst is approximately 10 to the 24. It is not 24 times, it is 10 to the 24 times. Million times, million times, million times, million. So this ratio between the electrical conductivities of these two types of elements is million times million to the 4. Or 1 million 4 times 10 to the 24. Okay, so for example, if you compare some radii, for example, the radius of the Earth around the Sun in the solar system, the radius of Earth around the Sun, what is it? It is 1.5 10 to the 11 meters. So this is the Sun, and that is the Earth, and it is turning around it. So this radius, which is almost a constant, so this radius is 1.5 10 to the 11 meters, of 150 million kilometers. If you convert it to meters, it is this much. 10 to the, forget about 1.5, it is 10 to the 11. So what is the radius of an electron in an atom, such as hydrogen atom? If we have a hydrogen atom, all right, so this is the nucleus, for instance, and here is the electron. Assume in Bohr's model, assume that it has a certain radius, etc. So the radius, whether it is turning in an orbital way or any other theory, but the important thing is the radius of an atom. The radius of an atom is on the order of angstroms. Let's say 1 angstrom. What is angstrom? 10 to the minus 10 meters. So if you divide these radii, which are extremely far apart, you get the ratio of 10 to the 21. So this ratio, radius of the Earth, radius of the electron. So radius of the Earth divided by radius of the electron, for instance, is approximately 10 to the 11 over 10 to the minus 10. So it is approximately 10 to the 21. Even this huge ratio is 1,000th of the previous ratio. So the ratio between the best electrical conductivities of the best ones and the worst ones is even 1,000 times larger than the ratio of the radii of the Earth around the Sun and the electron in a certain atom. So it is such a huge ratio. First of all, I should say this. Next, we should go a bit backward to the band theory of atoms. band theory. Instead of a semiconductor, let us first consider a metal, a simple metal, such as sodium that we have already considered to some extent. Sodium. That metal, sodium, which is called a simple metal, has, of course, as we know, 11 electrons. And the electronic configuration is 1s2, 2s2, 2p6, 3s1. So 1s2, 2s2, and 2p6, and 3s1. So as you see, there are, in this configuration, there are 2 electrons there, and 2 also there, 6 in the 2p state, and the outermost one corresponds to 3s, orbital 3s. So this is a sodium atom. If we have 2 sodium atoms, only 2 sodium atoms, infinitely far apart at the beginning, let us have 2 sodium atoms infinitely far apart. Infinitely far apart means they do not affect each other. But as the distance between them, as they get nearer and nearer, these orbitals, these electrons will start to affect each other. There will be some interactions between especially between the outermost levels. Let's say in this case, if they are infinitely far apart, there is no interaction. For example, assume that they are infinitely far apart. And especially the outermost, as they approach each other, approach in this case is supplied by some external agents. Let's say we are making them nearer. As they approach each other, especially the outermost levels start to interact. The outermost electrons of each one start to affect each other. Outermost electrons start to interact. And let me draw a certain plot for this case. Let me call this one separation, so the distance between them. So, for example, this one, which is the 3s level, will split into 2 as they are getting nearer and nearer. So that this one will split into 2. We have already been talking about the lattice constant, lattice parameter A from the beginning of the course. Lattice parameter. What is the lattice parameter? In a certain crystal, if the atoms are at, not if, but of course, in a certain metal in a crystal, the atoms are placed periodic in the sense of distance. So A is the lattice constant, which is the distance between two neighboring atoms, ions. So when they get to a distance of A, which is the lattice constant, but we only have 2 atoms. This is not a realistic case, not a metal, of course, not a piece of metal. We are talking about just only 2 atoms of sodium. And for example, this corresponds to that value of A. A is the equilibrium. A corresponds to A is the lattice parameter or lattice constant. At this distance between the two atoms, we have, as you see, two different values for the energy. So two states. So initially there was only one, 3s for each. Now as they get nearer, we have two possibilities for the outermost case. So it splits into two, start to interact, and the energy or the 3s state splits into two because we have two atoms. If we had 5 atoms, for instance, if there were, let's say, 5 atoms, what do we expect? We expect this level 3s to split into 5. If we have n, it has to split into n. And for instance, for a case of 5 atoms only, again, at the beginning, we go from right to left, from greater separation, leftward. For great separation, infinity far apart situation, we have only one level, of course, for each atom. Now we go from right to left, which means we are making them nearer and nearer. So this one now splits into 5. Again, at the level of equilibrium value A, we have these different states. 5. If you have and in those cases, n is a very large number, on the order of 10 to the 29, for instance, per cubic meter. We know that in a metallic object, for instance, capital N is, on the cubic meter basis, we have almost 10 to the 29. So if we have such a large number of atoms brought together, then this level is split into n very nearly spaced neighboring states. Okay, so this one is now divided into, split into n such states. For n atoms, we have the following case. At nearly infinity far apart situation, we have a single level, but this one splits into such a band. This is called a band because, yeah, there are of course slight differences between these successive energies, because as we said before, no two of them can take the same value, or no three of them, no four of them, because one energy for one particle. You have to multiply by 2 because of the opposite spin. However, we assume this is just one level. So this level, for instance, it is split into how many levels? N. What is N? A typical value. This is split into N levels, and N is, for example, on the order of 10 to the 29 per cubic meter, for instance. A certain finite band difference is now split into such a large number so that it is quite difficult to discriminate between the successive energy levels, even on the electron volt scale. Now let's compare the levels, how they split. First of all, for different infinity far apart atoms, we have, let's say, 1s1, 3s1 for one, and 3s1 for the other. This is the 3s1 electron and 3s1 electron for two infinity far apart sodium atoms. But if they are now brought together, so we have we have two possibilities, as we said previously. And these electrons now take this bonding state at a distance of A, equilibrium separation, lattice constant, lattice parameter A. Now with these two sodium atoms, the outermost electrons of these two atoms take this position, relatively smaller in the energy, because there is also one more state. Now let's compare the degree of splitting for the levels 1s, 2s, etc. For example, we have, remember, in the electronic configuration of sodium, we have what? Let's call it 1s, 2s, 2p, and 3s. And this is after the splitting for n atoms now. We don't have two, but we have n atoms. So many atoms are brought together to form the crystal. And then there was only two. 1s2, 2s2, 2p6, and 3s1. So this one, for the 1s state, this one, a bit larger, 2p is still larger, and this one, for the outermost, larger. But now, what is the capacity? What is the level of occupation? Let's say, what is the capacity? We have 2n, capacity 2n, totally filled. For the 2s, capacity 2n, totally filled. In the case of 2p, capacity 6n, totally filled. But in the case of the outermost one, 3s, capacity is expected to be 2n, but it is partially filled because there is only one electron coming from each atom. So half of the capacity is filled by electrons. So there is still empty space. Empty space doesn't mean the space to move. Empty possibilities, allowed possibilities. So this is, let's say, partially filled. Capacity 2n, partially filled. Not totally, but partially filled. That's why it's a metal. Remember the Fermi-Dirac distribution that we talked about last time. Today also we will refer to that and use it. Each energy can be obtained only one particle. By two because of spin, but let's assume it's only one particle. Let me emphasize the idea with a very simple example again. For example, if you are, let's say we are 100 people and we will go out for a drive, and all of us have our cars. We have 100 people, 100 cars. But what is the rule of driving in a certain region? They say that only integer values of speeds are possible, and one speed cannot be shared by two people. For example, starting from 2.6 kilometers per hour is not allowed. Only 1, 2, 3, it's up to 99 and 100. So these are the allowed values of velocities. 1, 2, 3, up to 100. And we are 100 people, we have 100 cars. For example, if I am the one driving at 24 kilometers per hour, by just a simple acceleration. I cannot go to the 25 kilometers per hour value because there is already someone there at that moment who is driving at 25 kilometers per hour. Also similarly, I cannot reach the speed of 56 kilometers per hour because there is already someone moving at 56. So we are sort of placed in our allowed values at that moment. But during the course of time, they may change. How? If the one moving the fastest of us, moving at 100 kilometers per hour, he or she is free. If he is allowed, if he finds enough energy, for instance, that electron having the greatest energy, remember it is the Fermi level, Fermi energy for the system, the greatest energy, at 0 Kelvin, of course. But at a larger temperature, for instance, if that person moving at 100 kilometers per hour moves to 110 kilometers per hour, all right, it is possible. If he finds energy, sufficient energy, he can do it. And then 100 kilometers per hour is left behind. There is no one moving at that. So someone, for instance, most probably the nearer ones, 99, moving at 99, 98, 95, can find, if that person can find the necessary difference in the energy to go to the state of 100 kilometers, but then it is also possible. Then there will be also a place left behind. So by this method, so gradually those lower speeds, other people moving at lower speeds, can go to reach the higher velocity. But at a certain moment, there is only one person moving at 74 kilometers per hour, one person 73 kilometers per hour, and all the way down. So it is, of course, almost impossible for the one who is already moving at 1 or 2 kilometers per hour to reach those high speeds. In order to reach those high speeds compared with their initial velocities, they should have a very large energy coming from outside, and it is really quite difficult. Because in some cases, if you have to either heat up the object, especially in the semiconductors, or give some optical energy, send some photons, etc. So if you want to increase the temperature so that it will be an insulator can become a conductor, and then theoretically although that seems to be alright, but in practice such a high energy may cause the bonds to break. Therefore the object will melt down without being a good conductor. So this is the main idea. And please don't forget that for a metal, simple metal, having empty place possibility in the outermost state, let's say 3s or 5s, whatever, 4p, in those outermost states, if there is an empty possibility, then if you unite those and of such atoms, there is still some empty place. Empty place in this case corresponds to vacant energy states. So this is the general idea. And if you compare these, for instance, also in this kind of picture, so these are, for instance, at infinitely far apart position, 1s, 2s, 2p, 3s. So that this is this splits into some band. This splits into a bit larger band. This is to a larger band, and this is the largest. So as you go from down to top positions at the equilibrium separation lattice constant A. So as you see, these are getting gradually wider and wider, those energy states. All right. So we have seen that in the previous lecture, in the free electron theory, we have seen the particle in a box problem, infinite well, infinitely deep potential well. For the infinitely deep potential well, for the infinitely deep potential well, we first started with the one-dimensional case, and only in the case of one-dimensional state case, we had a particle, let's say the electron, and the potential goes to infinitely high value, so it was impossible for the particle to go out of this well in which it was trapped. And the energy levels in such a system were discrete, quantized. So not all energies were possible, only some levels. What was the formula for the energy? That energy turned out to be h bar squared pi squared over 2mL squared. L is the disk length of this one-dimensional box. Let's say on the order of some, if you talk about the crystal, it is on the order of some maybe centimeters. If you consider only an electron in an atom, it is on the order of some angstroms, nanometers, etc. So it's very small, relatively small value. So these energies, En is this quantity multiplied by n squared, as we remember. And these n's, n takes values 1, 2, 3, integer values. So that in each case you have to take the square. So the allowed energies for such a box are 1, 2, 3, 4, 1. So this is E1, that is E2. This is 5, 6, 7, 8, 9, etc. So we have seen these cases. But then, to go more realistic, we move into two-dimensional box, which is like the surface of a billiard ball, pool table, where the balls are trapped in a certain surface. They cannot go outside normally. But it is not a single line like the bead which can move slightly along a wire. But now, in the two-dimensional case, this was the situation. There was a box, remember this was the x-axis, y-axis, alright, and this is the region. And in that region, let's say it is a square box of L by L. And in this case, the energy levels are, again, integer, quantized, discrete, but instead of a simple n squared, we have the sum of nx squared and y squared. And again, E is equal to some quantity, let's use h bar squared, pi squared, etc., 2m l squared, but we now have the sum of two terms, nx squared plus ny squared. Again, these are integer values, starting from 1, because 0 is meaningless here. Starting from 1, so the lowest value is 1 times that, next one is 2 times that, 4 times, 9 times, 16 times, so n squared. But this, in this two-dimensional case, it goes as 1 plus 1, which is 2. 2 squared, 4 plus 2 squared, and only one of them is 2, the other one is 1, so 4 plus 1, 5. Or 1 plus 2, 4 plus 1, 1 plus 4, they are degenerate states, as I said before, so they correspond to the same energy, so these are degenerate, etc. These are also some discrete states. In the most realistic case of three-dimensional box, we had a slightly different result. Let me now analyze that. In the case of the three-dimensional box, what do we mean by a box, by the way? If you have a piece of metal, for instance, let's say like a small dice, 1 cubic centimeter, very, very simple object, metallic object. This is a crystal, and it's a three-dimensional potential well, because an electron inside, of course there are billions of electrons inside, but assume there's only one, an electron inside cannot find enough energy to go out of this box, because the outside is energetically infinitely high, and it has to have that much energy to get out of the box in which it was trapped. So let's consider the three-dimensional case. Three-dimensional box. Again, we have a cubical box, for instance, L by L by L, X, Y, Z. So there's a particle inside, and that energy formula turns out to be this energy. It depends on three quantum numbers. So n, x, n, y, and z, and that corresponds to the same basic unit, this parenthesis, so h bar squared pi squared over 2ml squared. Multiplied by a combination of squares of these parameters. It is nx squared plus ny squared plus nz squared. And as we said last time, the possibilities are nx, ny, nz, and let's compare the energies. Energy multiplied by the basic unit of this quantity. How many times this quantity? So starting with 1, 1, 1, lowest state. So we can have only, some of them will be 1, 3. 3 times that. Next one is, let's say 2, 1, 1, 1, 2, 1, 1, 1, 2. But these three have the same energy necessarily, because the sum of 4 plus 1 plus 1, 6, the sum 6 can be obtained by 3 ways. There's no difference in free space between nx, ny, nz, etc. So this is 6. And if you continue further, you will have greater and greater values, as we said in the previous lecture. But now, we can place 3 electrons, or 3 times 2, because of spin you have to multiply by 2 every time. So we can place, let's say, 6 electrons in the first state. First state is this. Second state. Now we have, let's say, 3 possibilities. This is one possibility, so we can place 2. Sorry, this is the energy. How many possibilities? Only 1. There is only one state for which all n's are 1. However, we multiply by 2 for the spin. But if one has upper spin, up spin, the other has down spin, so we have to multiply by 2, that's all. Spin is not directly related with this topic, so I'm just skipping it. Maybe in a modern physics course we can have more, quantum physics course we can have more about it, to say. So, in the second case we have how many? 1, 2, 3. Forget about energy, we don't look at the energies. How many electrons can we place, allocate there? So we have only 1, but we multiply by 2. We can place 2 electrons in state 1. Okay, so this is, let's say, state 1, state 2. And we can place, this is a 3-place state, so we multiply by 3, 2, you get 6. We can place 6 electrons in state 2. But it is impossible to make such a calculation by hand, because we have to deal with 10 to the 23 per cubic centimeter. So since we have to deal with numbers like 10 to the 23, we have to deal with numbers and approximately, let's say, 10 to the 23 per cubic centimeter, for instance. It is impossible to make such a calculation. Instead, there's a maybe a clever way, smart way for these allocations. Because it is maybe as in a hotel reception, you have some rooms and you have some guests. How many people? Your customers are n people. You have n rooms, maybe n customers, n rooms. So you have to allocate them, place them to the rooms. But each room can accommodate one person or two people because of space. So each room you can put two people in a certain room, starting from the first stage, go to the nth stage in a very tall building. So this is a kind of placing those customers to the hotel rooms. But the number of rooms is very, very high, and the number of customers is very high. So let's find a better way of dealing with these large numbers. Let's draw a three-dimensional XYZ frame. But this is not XYZ, this is an X and Y and Z. The numbers be right here. For the quantum numbers, and sub X, and sub Y, and sub Z, let us draw a three-dimensional system. Let us draw a three-dimensional, let's say, system of coordinates. So this is an X, that's an Y, and this is an Z. And let's draw, not to make it too complicated, I will draw just one surface, one plane on this one plane and one plane. Of course, in between there are millions and millions of dots everywhere. So let me draw some relatively simple picture. So for instance, let's draw some lines here. And also at equal intervals. Also on the left hand wall. So let me draw this one a bit bold. So these are the main axes, and the other lines are, for instance, this is just like the XY plane, the floor. This is the wall. This is like the wall of the board. And this is like the other wall, which is perpendicular. So let me draw also the same lines there. And assume that there are dots everywhere. What are the dots? At the intersection point. This is like a grid. So in this grid, let's place the grid points. And we will be interested in how many points we have for a certain case inside. Of course, this doesn't end here. It goes to the infinitely large values. But we are interested basically in the near the origin. So this one, for instance, is a grid point. It's an intersection of two values. And for instance, nx equals, I'm not writing on the board, not to make it too complicated. But for example, along this axis, we have an nx. nx equals 1, 2, 3, etc. And y, 1, 2, 3. For instance, this dot, this grid point corresponds to nx equals 1, and y equals 1, and z is 0. And similarly, 1, 2, 0. Of course, z values are there, non-zero z value, but I'm not drawing it. It's impossible to draw it on a board like this. So I'm just leaving the others to your visualization. So these are the grid points, some of the grid points. And also here. So we have so many points. And these points, let me repeat, do not end here. They go to infinitely greater values in each of the three axes. Now let's consider a certain part of it. So, if you go beyond the wall, if you go beyond this board, we will have negative nx values, because nx will be negative there. If you go beyond this wall, ny will has to take negative values. If you go below this one, nz should have negative values. But negative values are meaningless for such cases. All these three quantum numbers should be positives. This is the condition. Since all these three values should be positive, since all of nx, ny, and z should be positive, we should consider only one octant of this spherical system. Octant, 1/8. Which 1/8? This one where all nx, ny, and z have positive values. First thing is this. Since all of x, y, z should be greater than 0, we consider only the first octant of this sphere. We consider only the first octant, 1/8, first octant of a sphere. What is that sphere? Let me draw now this 1/8 first part, first octant. For instance, let's draw these intersections. So this is the first octant of a sphere. You take a certain orange, for instance, you divide it into 2, again into 2 in the other perpendicular direction, and again into 2 in the other third possibility. So you have 8 identical pieces, 1/8 of a sphere, one octant. So this is the one. So for example, let me try to visualize it better. So we consider the first octant of a sphere. Divide by 2, by 2, by 2 in each of the perpendicular axes. Alright, if you start mentally, of course, these are some. Now this is the relationship between the radius of this spherical, hypothetical, of course, hypothetical surface. Let me repeat again. This is not a sphere inside the crystal. We don't have, these are not the atoms. Okay? Because so far, especially near the beginning of the course, we were drawing such pictures to give the positions of the atoms. These are not atoms. These dots do not represent atoms in a crystal, in a metal, for instance. They represent allowed values of quantum numbers. This is not x, y, or z. It is nx, and y, and z. What are those values? They are the quantum numbers in a three-dimensional potential web. So this is the radius of that hypothetical spherical surface having components nx and y and z. And since all of them should be positive, we consider 1/8 of this. But what is the volume of a sphere? Because each point corresponds to a combination of ends. But you can also consider that at each point there is a cubical box, for instance, right? So there is a cubical box around it. So at the next cubical box we have the next one, we have the next one, etc. So each one, let's say, each one of these, each one is surrounded by a, again hypothetical of course, cube. That cube has unit length. So how many cubes do we have in such a spherical volume? For example, you have a basketball and you place in it some cubical little objects, 1 cubic centimeter, like the die of backgammon. So we have cubic objects, but not randomly. We don't pour the set of dice into the ball randomly. We just place them in an arranged manner. So you place them, for instance, in an arranged manner. One cube next to it, the other one, etc. And those cubes are of course hypothetical because number of dots in that spherical volume is the number of cubes, because each dot corresponds to 1 cube. So what is the number inside? We have to find the volume. The volume of a sphere. What was it? 4/3 pi r cubed. But we don't have r, we have n max as the radius of that hypothetical sphere. The volume is 4/3 pi radius cubed. What is that radius? N max cubed. But as I said before, we should consider only 1/8 of this volume. So we multiply by 1/8. So totally, there's a cancellation of 1/6. So we get pi over 6 and max cubed. What is the number of electrons we can accommodate here? So we have so many rooms and so many customers in a hotel management. So many customers should be placed in the rooms of the hotel. So how many can we do it? If accommodate here, and is twice this number, because in each room we can place 2 people, and it times pi over 2 times pi over 6 and max cubed. So we have pi over 3. Therefore n is pi over 3 and max cubed. This is the relationship. Where do we use n max? We will use it in the energy, Fermi energy, for instance. Let's rewrite the formula for the energy. EF, that's the Fermi energy. It was h bar squared pi squared over 2m L squared multiplied by the combination of those quantum numbers. So we have nx squared, ny squared, and z squared. And this thing corresponds to n max squared. And n max squared is related with n by this expression. What is that? This is the expression. So n max is cubic root of 3n/pi. N max is 3n/pi cube root, because n max cube is equal to that. Alright, we need square, so that n max squared will be 3n/pi to 2/3. So let's put this quantity here and get the relationship between energy and the number of electrons in that system. So EF EF is equal to multiplied by this thing. What is that? 3n over pi to the power of 2/3. We can also put these pi and L inside this last parentheses. For example, if let's say a root b, for instance, can be written as, if you write a as a squared, you can also write them like this. So this is the algebraic idea. Apply it to pi and L. So pi squared can be entered here by to the power of 3/2. So if you, for example, here it is 1/2. A is raised to the power of inverse 1/2, which is 2. So we put it as a squared. The same idea is applied here, and we can write, for instance, EF is equal to that's the constant, h bar squared over 2m multiplied by 3, and now we have a pi cubed inside, because 2's cancel, pi becomes pi cubed, divided by 1 pi and L cubed to the power of 2/3. Now that we have one more refinement, it is the first we cancel one of these, so it becomes squared, and also we have L cubed in the denominator. What is L cubed? L by L by L. These were the sizes of the specimen sample, so that L cubed is just the volume V of the material, macroscopic objects. This is on the order of some centimeters maybe. So finally, we arrive at Fermi energy equal to h bar squared over 2m multiplied by 3 and pi squared over the volume to the power of 2/3. So this is the final expression relating the energy with the number of particles in the system. Let's have a very simple sort of example. For instance, find the value of Fermi level. Example, estimate the value of Fermi energy for a normal, ordinary metal. Estimate the value of EF, Fermi energy, for a metal. How can we find such estimations? Alright, EF is h bar. What is h bar? 1 times 10 to the minus 34. 1 times 10 to the minus 34, but squared. Divided by 2m. What is the mass of the electron? 9 times 10 to the minus 31. 9 times 10 to the minus 31. H bar squared over 10. Next, we have 3. N over V. N over V is the sort of concentration. It is, if you consider the cubic meter, it is on the order of 10 to the 29 for a metal. Remember that 10 to the 29 is a critical, is a characteristic value, typical value for a metal. But 1 over 10,000 of it, 10 to the 25, is a typical value for the concentration of atoms in a gas, molecules in a gas. 10 to the 25, 29. 29 for metals, electrons in a metal, and the 10 to the 25 is a typical value for the concentration of molecules in a gas, for instance, per cubic meter. So we can use 10 to the 29 for this ratio. 3 times 10 to the 29, and then pi squared. Pi squared, as you know, is 10 roughly, times a 10. No division. This quantity to the power of 2/3. And we can make an estimate, of course, easily. For instance, here we have 10 to the minus 68 coming from the first h bar squared. Divided by, we have a 2, but this 9 can be considered here, so it is roughly 10 to the minus 30, approximately, 10 to the minus 30. So we are here. 3, alright, not important. 3 to the power of 2/3, 10 to the 29, one more 10 to the 30, to the power of 2/3. So, these are not important. Forget about those 2s and 3s, not important. Power of 10 is, in fact, the most important part in calculations in physics, especially in such atomic or astronomical cases. We are not much interested in the number before the decimal point. So the order of magnitude, maybe positively, maybe negatively, the order of magnitude is the most important part. Please keep it in mind. So we have 10 to what? 10 to the minus 68. This 330 and it becomes 20 times 10 to the 20 and 10 to the 30 coming from below. So it is on the order of 10 to the minus 18. So it is roughly on the order of 10 to the minus 18. What is the unit? Joule. But since we said joule is too large a unit for such calculations, for the energy of atomic particles, joule is limited to some microscopic systems. For instance, if a ball is moving, if a ball of 1 kilogram mass is moving at 1 meter per second, its kinetic energy is 0.5 joule. But if you are talking about electrons, protons, some other atomic particles, subatomic particles, of course joule is too large. Instead we use electron volt, and we know the conversion factor, it is the charge of the electron. So if you divide it by 10 to the minus 18 divided by 1.6 10 to the minus 19, which is the charge of the electron, then the result is approximately some, let's say, maybe 1 to 10. It is something less than 10, 1 over, you can write it as, for instance, 10 to the minus 18 divided by 1 and 1.6 are not too different. So this is on the order of 10 to the minus 19, on the order of some 1 or 2, let's say, electron volts. So it is that Fermi level is indeed, it turns out to be on the order of electron volts by such assumptions. We made several assumptions to simplify the matters, but still we obtained a value of on the order of electron volts. And as we know, the Fermi energy for typical metals is around on the order of electron volts, as you will see in some other systems. Now another important thing is the density of states. What is the meaning of density of states? In statistical physics, in solid state, in quantum mechanics, the concept of density of states is important. We will make use of this when we calculate the carrier concentration in semiconductors, for instance, number of electrons, number of holes, etc. But basically, what do we mean by density of states? It is generally written by GOV. GOV, or in some books, maybe DOV, because in statistical physics we generally use DOV, density of states. GOV is also used. So it is a function of energy. As we will put this into calculations in number of carriers in semiconductors, it gives us an idea of the possible values for that energy. Possible means the allowed states. So let me first find it from this using the definition and then say a few words about it. So G of E here is a partial derivative of N with respect to E. How does the number change as a function of energy? Maybe you can consider it first after making a simple calculation here using this equation, because it is not valid only for Fermi level, it is valid for any energy. The important point here. Fermi level is a single value. It is the greatest energy an electron can have for a metal at 0 Kelvin. But this expression is not only valid for finding that single value of EF for any energy E. If there are n particles in the system, so this ratio del n by del E, partial derivative of the particles, concentration with respect to energy, can be, for this calculation, that result can be used. So what is del n by del E? Let's write it in a better way. For instance, take these there. 2m E over h bar squared is equal to 3n pi squared over volume to the power of 2/3. If you raise both sides to power of 3/2, inverse of this, so let's say we raise it to the power of 3/2, we raise it to the power of 3/2 so that they cancel. So we have just the remaining part here, 3n pi squared over volume, unit volume let's say, is equal to 2me over h bar squared to the power of 3/2. So just leave n here, just n is some numbers which are not too important. V over 3 pi squared. Also let me separate this into two parts. Energy is the important part and the others are constants which are not as important as energy. So this is 2m over h bar squared to the power of 3/2, and the important part is here E to the power of 3/2. So these are all constants. This is something like y is equal to some numbers a, x to the 3/2. So dy by dx is simply, let me say dy by dx. There's only one variable here. It is just a times 3 over 2 x to the 1 over 2. The same idea applies here as well. So as we expect, the result will be G of E. G of E will be some constants, not important too much here. And 3/2 also comes, and it is just E to the 1/2 square root of E. So let's draw a simple graph representing this behavior. For instance, if we have x-axis, y-axis, and we have the function y is equal to root x, this is the expected function. 1 corresponds to 1, 4 corresponds to 2, etc. So this is the square root of x function. So similarly here we have, for this case, we have energy axis and we have G of E axis, and the same behavior is obtained here. As the energy is increasing, which means as we look at the energies, higher and higher energies, the number of allowed places, states there, gets greater. But it is not linearly proportional, it is increasing but not as large as linear or square relationship, but in a square root manner. So we understand that G of E is proportional to density of states is proportional to the square root of energy. And we will make use of this when we calculate other things. We have also seen Fermi-Dirac distribution because we have to prepare, or we have to get prepared to understand for different versions or different aspects of the same thing, and then we will unite them when we get some other calculations. So this is one part. Density of state is one part. It gives us the idea of how the number of allowed places changes as a function of energy. But on the other hand, we should take into account the Fermi-Dirac distribution, which gives us the probabilities of those places to be occupied. For example, let me right now tell a simple example related with both density of states and the probability Fermi-Dirac, and then we will find them separately and unite. For example, if you let us assume that we have you are the owner of a large concert hall. Okay, so here is the stage. This is the top view of the seats, concert hall. You are the owner, and there are some seats. So these are the seats. Each seat can be sold up to one person. So these are, remember, fermions. Electrons are fermi. They obey Fermi-Dirac statistics. So in a certain place, in a certain seat, in a concert hall, in a cinema, movie theater, for instance, you can place only one person. Just like the parking lot of some cars. In a certain place, you can park only one car. There is no possibility, unless you have some stages above, for a normal open air garage or parking lot. You can park only one car in a certain place. Only one person can sit in a certain seat. This is the main idea, because if it were bosons, if we talk about the photons obeying Bose-Einstein statistics, of course it will be possible to allocate more than one particle in the same place. The same place here means same energy. As I said before, for the driving a car example, there is only one person who can drive at, let's say, 68 kilometers per hour, one person for 72 kilometers per hour. But if these are bosons, if they obey Bose-Einstein statistics, which we are not interested in now, then it is possible for several people to drive at the same speed. It is possible for several people to get the same same amount of money, as I said in the previous lecture. There are several pieces of money from 1 lira to 100 liras, for instance. So in that case, only one person could take, let's say, 38 liras. One person could take 84 liras. However, in this case, in the case of bosons, there is no such limitation. But here we have limitations because fermions are, and electrons, protons, neutrons, these obey Fermi-Dirac statistics, and they are limited by the number of occupation per seat. In this case, seat means one energy value. So it is, let's say, increasing this way, just like this energy axis. The energy axis means the following, because the seats near nearest the stage are more expensive as you expect, obviously. Okay, these are more expensive. The back seats are cheaper, of course. So expensive means large energy. So these are cheap seats which have low energies. According to this picture, I have drawn something in a similar way. So number of seats for the cheap case is less because these seats correspond to somewhere here, lower energies. But the expensive ones correspond to greater and greater energy values. This is one aspect of the story. But there is one more aspect, which is the probability. Yeah, there are so many states at higher and higher energies, but can we sell them easily to people? Because since this seat is more expensive than the others, maybe it will be quite difficult to send those relatively expensive tickets to the people. So that one side of the story is G of E, change in the number of seats allowed as a function of energy, just like this price of the ticket. And the other side part is the F of E, Fermi-Dirac distribution, which gives us the probability. And now let's consider this one separately, and then we will join them in an integral. For the Fermi-Dirac distribution, remember that we have drawn a rectangle first. Fermi-Dirac distribution, again, Fermi-Dirac distribution revisited. Now it will be drawn as, this is the energy axis, that is the F of E axis. Now in this case we are dealing with the probabilities. Let me write the expression for the distribution. F of E, remember, was 1 over e to the e minus ef, e sub f, divided by kbt plus a 1. So this expression gives us the shape of this. And it gives us the probabilities. What is the probability of, let me write it as a sentence, f of e gives the probability for finding an electron, having energy E, for finding an electron having energy value E. Whatever energy we are interested in, if you put that value here, this gives us the probability 0.5, 0.2 to 20%, 10%. Okay, so we are interested now in the between the limits of 10% and 90%. So let me write it here. So this value corresponds to E, this is also E, and these axes are F of E and G of E, as we have found. F of E, this function, is the probability, the upper one. It is like a rectangle at 0 Kelvin, but that part is modified. So it means this area is almost equal to that area because these electrons now have greater energy. So these positions are empty, vacant states, but they have moved to a bit greater energy, just like the driver moving at 100 kilometers per hour. Now he finds enough energy, so now he goes at 110 kilometers per hour. But there's no one now moving at 100 kilometers per hour. So this is the same idea. On the other hand, this is the idea of the concert hall tickets, etc. So that as E increases, G of E increases, but in the way of square root dependence. Alright, so let's, this critical value is EF. This critical value is the Fermi energy. Now, F of E is equal to 0.1. If you put 0.1 on the left hand side, what do we get for the E minus EF? Not just E, but E minus EF, that difference. If you set it equal to 0.1, 1 over E to the E minus EF over KBT plus 1 is 0.1. Now after this simple operation, we have E to the E minus EF over KBT plus 1 is equal to 0.1. Take it to the other side as minus 0.9. Take the lns of both sides, lns of both sides to get rid of the exponential. We have E minus EF is equal to, let's take KBT also, KB times T ln minus 0.9. But minus 0.9 means what? Minus 0.1 over ln minus 0.9. What is that? It is just minus, because ln 10 is 2.3. ln 9 is approximately 2.2, but it is negative. So that one is corresponds to that. Roughly 2.2. So that E minus EF is equal to KBT is, remember, 1 over 40. 1 over 40, because we are now at room temperature, 1 over 40 times minus 2.2. So this is approximately minus .01. 002, sorry. Yes. 1 over 40 times that. So after this operation, we have exponential part minus 0.9. Just this difference is take the ln, alright, KBT ln minus 0.9. 0.9 is ln 0.1 minus 1. So ln, this ln corresponds to roughly 0.5 or so. So let's do it in a better way. Because the same will apply for the other part, for the 0.9 case. So let's find it better. This one is equal to 0.1. First, 0.1. So we have 0.1. The exponential part is minus 0.9. Take the lns. Okay. So the E minus EF, that difference is KBT times ln minus 0.9. And this one we can keep it. For F of E is 0.9, the other value, 0.9. Let me do it here. E to the 1 over energy difference plus 1 is now 0.9, the other extreme, so that we have, there's also 0.1 here. There's also 0.1 there. So, if you make this operation, simple operation, we have 0.9 e to the something energies plus 1 is equal to 1. So we have 0.9 times exponential plus 0.9 is equal to 1. So that we have 0.9, the exponential group is 0.1. So that exponential part is 1 over 9. And then exponential part. Take the lns of both sides. So that ln of minus 9. Alright. So E minus EF now will be kBT times ln 9. Here I've forgotten to multiply this by 0.1 here, so that there's a little error there. Alright, now we have E minus EF is equal to kBT times plus ln 9. Here we have E minus EF to kBT times minus ln 9. But ln 9 is approximately 2.2, so that let's consider here. So we are interested in these values. So this point corresponds to EF minus, by the way, 2.2, 4.4. So that difference, this difference is now kBT times, so ln 4.4, so therefore 4.4. This is approximately 0.1. 4 over 40. So this is 4.4, this is 1 over 40. So this is approximately 0.11 or so. That part is corresponding to, so these are the electrons having probabilities between 0.1 and 0.9. And what is that number? It is approximately a few percent. How do we know? Because this part corresponds to 0.1 electron volt. But what is this value of EF? It is, for instance, 3.2 electron volts for sodium, if you are talking about. So that it is around that part. And this part is corresponding to a few percent. A few percent. So the more important ones, more important in the sense that these are creating the conductivity, for instance, thermal, also a specific heat. Remember that for the specific heat of electrons, free electrons, the classical theory says that it is 3 over 2R. 3R coming from the ions, atoms. 3 over 2R, half of it, comes from the, should come from the free electrons in a metal, for instance. However, that contribution from the free electrons was almost 1% of the expected value by the classical theory. What was the reason? This is the reason. Because these are just a very little percent of the whole number, which can provide some conductivity, electrical, thermal, specific heat also, for the case of specific heat. So a few percent of the electrons can give contributions to the conductivities in the new modern theory. But in the classical theory, they assume that all the electrons are ready to give contribution. However, they are not. Just a few percent of them having energies near this limit. They are only a few percent, maybe 1 or 2%, 3% of the whole number. That's why the values of conductivity or specific heat were much less than the expected value by the classical theories dating back to the 19th century. Now let's consider the semiconductors. These were for metals about band theory. This was the basis for the band theory because we have bands now. What is that band? Remember that if they are sufficiently far apart, infinitely far apart, this is the separation between them. At large separations, they do not affect, they have no interaction. So that these states are discrete states. However, if they begin to gather, to combine, to form a crystal, for instance, then they are interacting with each other. So that those 3s, 3p, 2p, whatever states, they also split into number of atoms. And if that number is very large, such as n, you cannot discriminate between the successive energy values. For example, this is a line. If I divide it into centimeters, one by one, it is easy to understand, to observe these separate marks. But if it is possible for me to draw lines at, let's say, nanometer level, for instance, then of course you cannot determine the number of marks along this line. If this is divided into 1 billion pieces, you cannot distinguish between two neighboring marks. It is now divided more than 1 billion, for instance. Okay, billion is 10 to the 9. This is divided into 10 to the 20s. So it is impossible to distinguish between these successive neighboring energy levels. Delta E, DE, these are separated by some very small amounts of, even on the electron volt scale. Alright, for the large separation, there are separate levels. Now let's talk about semiconductors. Because band theory for the metals explains why some materials are good conductors and why some are bad conductors or even insulators. Because, for instance, here for a metal, for instance, for a metal such as sodium, as we have seen, this was the 3s level, and half of it, after they split into that and they formed, this part was filled and this part was empty. So if one of these finds enough energy, it can move to the empty part and then it can give contribution to the conductivity, for instance. However, if this is totally filled, if this were totally filled, it would be impossible for these electrons to be moving, promoting to higher states. There is no higher state allowed for that. Alright, now let's consider some, for instance, carbon. Carbon, diamond, silicon, they have all the same atomic structure. So let's consider, for instance, carbon, 1s2, 2s2, 2p2. So this is 2s and 2p levels, for instance. Let's say 2s and 2p levels for separate infinitely far apart atoms. We have discrete, separate levels. However, as we go from right to left, it means as we make them nearer and nearer to form a crystal, and n of them, of course this will be split into a band. But this will also split into band. So this is also such a band, and these are such bands, 2B band, 2S band. And for this critical value of A, that is constant, such a separation where this crystal is formed normally, this is the average spacing between successive neighboring atoms. So here, as you see, there is such a gap. So this is the energy gap. It is also called forbidden band gap or forbidden gap or energy gap. Some energies cannot be obtained. Some, for instance, these energies, let's say these are the energies they correspond to. This is the energy axis. These energies cannot be obtained by any particle. These are these energy values cannot be obtained. How come is it possible? One may ask. Because normally we expect all the energy levels to be shared by or to be obtained by some particle. But in this case, it is maybe similar to this simple example of an exam. For instance, let's say we make an exam. We prepare an exam of physics, for instance, and ask only 4 problems. We prepare an exam and ask only 4 problems. But they are not worth the same. We ask 4 problems, 3 of them worth 1 point, and 3 are worth 1 point, and 1 is worth, let's say, 6 points. Such a strange exam because the other problem is, let's say, much harder than the others. And also, no partial credit is given. This is like a test type of exam, for instance, multiple choice, for instance. So that you either get full credit or nothing from a question. Okay, which grades can be obtained, which grades cannot be obtained? Can we obtain 1? Can we get 1? Yes, if you solve just one of these. Yeah, these are 1, 1, 1 and 6 grades, points for problems. Can we get 1? Yes, because if you solve only one of these little easy ones and nothing else, you get 1. Can we get 2? Yes, if you solve 1 and 1, 2 simple problems, you can get it. Can you get 3? Yes, if you only solve these easy problems, but not the hard one, you can get 3. But can you get 4? No, impossible. Because 4, similarly 5, cannot be obtained. 4 and 5 cannot be obtained in such an exam. 6, yes. 6 can be obtained because if you solve only the hard one, not the easy one, you can get 6. 7, also 6 plus 1. 8, also 6 plus 2. 9 totally, or if you solve all of them, you get 9. However, there are some values which cannot be obtained. So this gap is similar to that. A particle can have one of the lower energies, if possible, one of the higher values, but not anything in between. So this is the idea of gap, forbidden band gap, because this part is forbidden. It is not allowed for the particles to have one of these energy values in the very simple sense. Of course, there are several subtle points, details, but in the very simple sense, this is the idea. Allowed values, also allowed values, but forbidden values. And if you consider only this part in a very magnified manner, so you can basically have such a picture. So this is the energy axis. These states are full. This is empty at the beginning at low temperatures, for instance. This value, the critical value is E sub V. This one is E sub C. EV is the valence band. EC is the conduction band. The valence band is VB, conduction band is CB. But these values of energy EV and EC are the valence band limit, because it starts from, it ends here and the other starts there. So this part is called EG, energy gap. So this corresponds to energy gap. So in the following calculations, we will make use of this gap also. So the main idea, whenever we see such a picture, we should understand that we are talking about this part, that narrow part. So some values are possible up to some value. So this, for instance, this corresponds to energy valence, that corresponds to energy conduction, and in between there's a gap. No electron can have these energies normally. In semiconductors, we will also have the Fermi energy. But F of E, remember, F of E was written, it has the same definition, of course, same formula. Same formula, but where should we put EF? Because for the metals, for metallic objects, for instance, EF corresponds to where the probability is 50%. For metals, EF corresponds to where F of E is 0.5. And remember the picture, this was either a rectangle at 0 Kelvin or some deformed version. But every time, this is the fixed point where the curves are passing through, so that EF is 0.5, EF corresponds to 0.5 for the function. Function is the probability. But as we have seen now, there's a gap. And below the gap, all the states are occupied. Upper the gap here, so this is the picture, very simplified version. Remember, this corresponds to the valence band, largest energy for the valence band, and this is the smallest energy for the conduction band, and that is the energy gap. But where is the F? For example, below these, there are, let's say, these circles represent electrons, but those electrons are not free. They are still attached to their host atoms, valence. But here, if there is an electron, it means it is something which is freely wandering around. But there is nothing in between. None of these energies can be obtained by a particle. So where is 0.5 in such a system of semiconductors? Because this was alright for metals. Now, by convention, the middle point, midpoint, halfway, is assumed to be EF. So that EF corresponds to approximately EG over 2. So this, please keep in mind that in semiconductors, Fermi level, Fermi energy corresponds to half of the gap. And these gaps are generally on the order of a few electron volts. If, for instance, if EG is less than 3 electron volts, we call it a semiconductor. And if EG is greater than, there's no clear-cut separation between them, but roughly, the interface, there's no certain interface between these two regimes, but if it is on the order of but less than 3 electron volts, it's called a semiconductor. If it is something greater than that, it is called an insulator. Semiconductors, insulators. For instance, diamond, silicon. Let's compare them. Energy gap for silicon is 1.1 electron volt. Energy gap for the germanium, which is also very important type of semiconductor used in applications. This is 0.67 electron volt. But energy gap for the diamond, a kind of carbon, because the structure is, it consists of carbon atoms. Diamond is, let's say, approximately 5 electron volts, 5.5. But these are at normal temperatures, all right, at room temperature or low temperature, for instance. These are sort of, they create some conduction. Not as good as a metal, but these are sort of bad, but conductors. However, here, diamond is a very good insulator or very bad conductor in the other sense. However, the difference, let's compare them, all right? Let's draw two pictures. Assume this is for silicon, this is for diamond. This length, okay, let's say EG is equal to 1.1 electron volt energy gap, because this corresponds to valence energy, this corresponds to conduction band energy. Now, if you compare it with that of diamond, and this is the corresponding valence edges, but this is 1 unit, 1, 2, 3, 4, 5. Let's say the gap is this much. The gap is this much for the silicon and that much for the EC, for the diamond. Do we have a huge difference? No. That ratio is almost 5 times, 5-fold difference. Okay, 5-fold. So we can normally expect that the conductivity of diamond is maybe 1/5 of that of silicon, maybe expected. However, it is totally wrong, this expectation. The ratio of the gaps shouldn't give us this doesn't give us the value, the result for the whether this is conductor or insulator, because there's an explanation. These values, EC, E gap, appears in an exponential, and the exponential function is by far the most powerful one in mathematics, much more than the polynomials, much more than other functions. Exponential, positive and also negative. A positive exponential, let's say in e to the power of x or e to the power of minus x. These are exponentials which are much more powerful than other types of functions, and we have here an exponential there. So although this ratio of the gaps between silicon and diamond, a semiconductor and an insulator, this ratio ratio, okay, this Eg of diamond divided by Eg of silicon is almost 5-fold. However, we cannot conclude from this idea information that the conductivity of diamond is 1/5 of, or let's say 1/100th of that of silicon. Why? Because we have an exponential function. We will see when we get the real numbers for these n's, the number of concentrations, we see it in a better way. Not now. Alright, let's also consider the temperature dependence. How does temperature affect these number of carriers, free number of carriers? And for instance, first of all, let me show the electron hole pair. And this is the picture, energy, conduction, energy balance. And say that these are the electrons for a semiconductor, for instance. These are the electrons, a valence band electron. What is the meaning of a valence band electron? This electron is just staying in an atom. It is not detached from the atom and moving around randomly, so it doesn't give any contribution to the conductivity, for instance. Alright, if this much energy, remember this much was Eg, energy gap, if this much energy is given, supplied to one of them by some means, by which means? Either by heating the sample, increasing the temperature, or by optical means. Optical here means a photon sent to the sample having enough energy, as I will try to draw soon. But now, by some means, for instance, let's say heating the sample, let's say if an energy Eg was the necessary difference, if energy Eg is given to the semiconductor, SC semiconductor in this case, then let's say one of them is excited, promoted to the higher level. So then, let's say one electron, one valence band electron is excited. And for example here, there's an active place, and this thing is now excited to the upper band. Now it is somewhere here. So here it is a free electron. And free electron, so it is ready to give some contribution to the conductivity of the sample. If you give some more heat, then maybe this one will also be excited, etc. But if you give some energy less than that gap, it is impossible to be promoted there, and it still stays in the valence band. So the minimum value necessary is this much. So E minimum is, at least it should be as large as E gap. For that material. For silicon it is 1.1. For germanium it is 0.67. For some other object it is that much. But for diamond, for instance, and by the same idea, for diamond, if we give the electrons here this much energy, then it is expected to be a conductor. However, this much energy corresponds to maybe 40,000 Kelvin temperature. So until this becomes a conductor, the object melts easily. So these insulators can never become conductors if there is such a gap more than 3 electron volts, wider than 3 electron volts, it is impossible to make them a conductor. Alright, this is the main idea. And here we have an electron-hole pair. So if you consider these, this is an electron-hole pair. In short, it is sometimes written as EH. What is a hole, by the way? Hole. For instance, let's consider a piece of a group of eggs. So there is, let's say, such a group, and there is no empty place for this, for anything to move. If I create an empty position, vacant site, let's say, let me take one of them. Okay. So now we have a free place to go for the others. For instance, if I move this one step further, without breaking it, the empty place in the first position now moves backward to the second. If I move this one step further, that hole at the front initially now moves to the third position. If I continue to do this kind of transportation, that hole moves back. And finally, if I take this one also to the new position, then the hole which was at the beginning here now has moved to the a new position, and that hole has moved. Of course, the mobility of the hole, mu h, is less than the mobility of an free electron. It is maybe a bit more difficult to make the holes move than to make the electrons move, but never mind. It is a second possibility for the conduction. So conduction is provided by two items, by free electrons or by free holes. For instance, this is a hole pair. What happens to the crystal by this operation? For instance, we had as I've drawn previously, we have these atoms. And these atoms are connected by bonds. Let's assume this is the silicon crystal. And each circle is a silicon atom. And each of them is connected to the neighbors by bonds, covalent bonds. How do they form bonds? By the outermost electron. So each bond has, let's say, two dots. These dots are electrons. So each bond, there are two electrons in each bond. As you see, there are two electrons. For example, if you consider one bond, this is a bond. That's a silicon atom, that's a silicon atom. And this is from the lower one, that electron is from the upper one. So they make a covalent bond. So they are sort of connected together. Well, what's a hole, by the way? A hole is obtained if one of them, let's say this one, is not there anymore. This electron is not there. This electron is represented by this picture now. So that this electron is now freely moving in between. How do we represent this operation on this energy diagram? This position was the previous position initially. Now that electron is now free. It gains by some means some energy, and because of that energy difference, it gains the necessary amount of Eg. So it is promoted on the energy picture, it is promoted to the higher upper band and conduction band, so it's a free electron. But in the crystal, what happens? This electron is not there anymore, and it is now wandering around inside the metal or semiconductor, the object, the sample. So this is the idea. And what about the temperature dependence? We will also see the temperature, but let me show this by another means, because this excitement, or this excitation. The excitation here means creation of an electron hole pair, creation of an electron hole pair is obtained in this case either by heating the sample or by sending some photons. The excitation is obtained or can be obtained by heating the sample, in other words, increasing the temperature, or by sending some optical agents, or by sending photons. But there's a condition for this. Sending photons having energy E greater than or equal to energy gap. If you send some photons having energy this much, it is not enough to promote this electron to an upper band. So it should have, the photon should have an energy at least equal to the energy. And E, remember from other courses, maybe energy of a particle is hc over lambda, h nu. So E is, for instance, is h nu for a quantum particle. Nu is the frequency, h is Planck's constant, E is h nu. But also it can be written as h c over lambda. So that h nu minimum value of frequency should at least be equal to energy gap. Or lambda is max. In this case, if h is min is there, lambda h minimum corresponds, minimum frequency corresponds to maximum wavelength. So that nu min for the photon corresponds to lambda max, minimum frequency, maximum wavelength, and vice versa. Alright, so h minimum, h times nu minimum is Eg. For instance, what should be h nu minimum? For a case of silicon, for instance. For silicon, let me just get an order of magnitude. For silicon, we have seen that Eg is around 1.1 electron volt. Okay, 1.1. What should be the minimum frequency of the incoming photons if we have to excite these electrons of silicon? H nu min is 1.1, but electron volt. Let's convert it to joule, for instance. So it is 1.1. In order to convert that, we have to multiply by the charge. Times 1.6 times 10 to the minus 90. So many joules. But we have nu minimum is equal to this one divided by H. 6.6 10 to the minus 34. So what do we get? Nu minimum should be, let's say this is 1 over 4, roughly 1 over 4. Roughly 1 over 4, but what is the power of 10? Minus 19 plus 34. 10 to the 15. Let's say 10 to the 14. Nu minimum is approximately 10 to the 14 hertz. This is the minimum frequency for the incoming photons if we should create an electron hole pair for silicon. For germanium, for any other semiconductor device, material, energy gap will change. For example, in the case of germanium, it will be 0.67, less than that, so that mu min will be less than that, maybe half of it. So this is the really important, one of the important relationships, because there are just few relationships, few equations in this course. This is one of them. What about the temperature dependence? Let me continue. The temperature, as you see from the formula, which formula? Fermi-Dirac distribution. So, as we see from the distribution, 1 over e to the e minus ef over kBT plus a 1. As you see, there is a ratio. If you increase the temperature, this ratio will be smaller. But it is the power of the exponential exponent. As this ratio gets smaller, exponential will get smaller, so that this function distribution will be larger. So as you increase the temperature, probability of finding some electrons at higher, relatively higher energy values will be more and more. So that it is unlike the metals. Be careful. The conductivity, for instance, or resistivity, whichever you like, the behavior of metals and semiconductors are different, opposite as far as conductivities are concerned. For instance, let me draw a simple picture to compare. Let's say this is the temperature, and that is the, let's say, resistivity, or conductivity, whichever. What did we learn for the resistivity of a metal? And it was, let's say, such a relationship. But be careful, we put resistivity, not conductivity. The resistivity of a metal, alright? This is a metal, okay, case of the metal. Resistivity was almost linear, including room temperature here, but it doesn't pass through the origin, as I said before, because of some unwanted impurities, dislocations in the system, etc. Necessarily, there is some residual resistivity even at 0 Kelvin, so that this curve, this line, not a curve, line, this line, linear function, doesn't pass through the origin because of this, the presence of some unwanted impurities, other atoms, etc. We have seen it. But what about the semiconductors? Resistivity of a semiconductor is getting less and less. So let me draw some other picture, maybe like that. This is for a semiconductor. Or if you draw the conductivity, it's just the opposite. For instance, let me show it by a very simple picture. For instance, let's say this is a glass. This is a glass, for example, and we have a certain bulb here and some potential source. Let's say this is potential source and this is a glass. Normally, this is like an insulator. So no current, although there's a battery connected here, no current is passing and the bulb is off. The bulb is off, no light. However, if you put some heat source under the glass, if you put some, let's say, source of heat, if you heat it, now the light is on. Because you increase the temperature of this object, therefore it becomes more and more better and better conductor. And some current is passing through so that the bulb gives off some light. However, in the case of low temperatures, there is no, almost no net current passing through the glass. Okay, so In the next lecture, these are just some preliminary concepts. In the next lecture, you'll be interested in calculating the number of carriers, concentration of carriers, N and P for the semiconductors. The dopings, N-type dope, P-type doped cases, and we will how we put them in a device, simple device, diode, transistor, in a logic gate, for instance. How we put them in a sort of semiconductor device, and also we will see how the basic idea, what the basic idea of a laser is, and how a laser works in principle. So this is the end of the introductory part of semiconductors.